So I'm Emil, I'm a postdoc in Uncle's group, and I will tell you a little bit about what we've been working on for the last couple of years, both on the cavity engineering side, so trying to understand how a changed dielectric environment modifies material properties, but then also opening up the system and thinking about how you can do spectroscopy on these types of systems. And then in the end, I will present some open questions or some directions that we would like to pursue, but haven't really done in detail yet. So this is meant to be some sort of seed for the upcoming discussions. First of all, I would just like to acknowledge the team who has been working on this. So a lot of the work I will present is based on the work of Lukas Grunwald, who is a PhD student in the group. And then both Na Xinle and Chong Xiao are also working on these cavity-based systems in one way or another. So to just give a brief motivation, the reason why we want to look into this is, in a sense, trivial observation that you can do material engineering out of equilibrium. So by driving a system with intense laser fields in different ways, you can change material properties. This is, for example, evidenced in this experiment by James McIver's group on inducing a light-induced anomalous Hall effect, possibly driving a paraelectric to a ferroelectric transition and inducing magnetism by terahertz driving. And then the idea would be to see how you can transport this from a non-equilibrium to a thermal equilibrium situation. And this is the subject of cavity materials engineering. So what we wanted to do is to design a dielectric or electromagnetic environment for the system to modify its properties. And there's been some interesting experiments over the last couple of years showing that indeed these types of systems do show an effect. So there is this work from the group of Jerome Fais, where they've shown that you can modify both the integer and the fractional quantum Hall effect by placing the system in a cavity. And there's also this group or this work from the group of Daniele Fausti, where they show a very large change in transition temperature for the metal to insulator transition in tantalum disulfide. So in both these cases, it's very clear that the cavity does have an effect, but it's also clear that we don't necessarily understand why this happens. Should also mention there is now this very nice work from Dimitri's group on cavity-altered superconductivity, which should also go here. So from the theory side, what we want to do is basically to set up a general framework to address the physics of these types of systems. So in our formulation, this is based on starting from the so-called Pauli-Fierz Hamiltonian, where you have a system of interacting electrons and nuclei, which are both coupled to each other via Coulomb forces, but also coupled to a quantized electromagnetic field. And the key feature of this Hamiltonian is that it is bounded from below and therefore has a stable interacting ground state. This might seem like a not too important statement, but if we want to develop perturbation expansions on top of this, it's actually a key feature. Then there are different ways you can go about in trying to solve this sort of Hamiltonian. So one route is to develop a kind of density functional theory version for quantum optical systems, which is called QED DFT. And then basically what you do is to incorporate the effect of these fluctuating photon fields in a new term in the exchange correlation potential, and then you can solve for the electronic ground state of the system just as you do in standard DFT. It's also possible with this type of framework to include photon-phonon interactions. However, one weak point of this sort of setup is that DFT is usually limited to weak correlations. And what we would like to do is mainly to target systems with strong correlations. So an alternative route is then to try and map this Hamiltonian onto an effective low energy subspace. Practically, this is done by mapping the Bloch functions of the DFT result onto Van functions. But then we're left with a kind of generalized Hubbard model of this sort here. So we have some kinetic energy term described in terms of hoppings. We have some Coulomb interactions, some spin-orbit interactions. Then there is also in principle phonons and electron-phonon coupling. And then we can include light matter interactions both on the electron-photon side and on the phonon-photon side via these Pyle substitutions or by coupling to the Born effective charge or Raman tensor. And crucially, by working in close proximity with this QED DFT framework, it's possible to determine all the parameters of this Hamiltonian in such a way that we have a predictive theory for these hybrid light matter strongly correlated systems. So this will be the starting point for the cavity engineering that we're considering. Then since what I will be talking about is mainly magnetic systems, it might be useful to also do some additional transformations on the Hamiltonian to simplify it a bit. So what we usually do is to do a Schrieffer-Wolff transformation. So this is the usual transformation you do to go from a Hubbard type model with electrons and spins to a Heisenberg model with spins only. And then you can do this also in presence of cavity photons or basically any photon field. And you're left with this spin photon Hamiltonian. If we're further mainly interested in the long wavelength dynamics of the system, we can take the continuum limit of this and we end up in sort of an effective Ginzburg-Landau theory, but with interaction to photons still included. So as a brief example of how this works, I will discuss the case of iron phosphorus trisulfide and kind of an equilibrium version of nonlinear phononics that we recently proposed. So the basic idea here is to just look at the analogy between this typical Hamiltonian, which appears in nonlinear phononics, where you have some general electron-phonon Hamiltonian, and then you have a nonlinear phonon-phonon term where you couple an IR active phonon to a Raman mode. And then you further couple this IR active phonon to an electric field. Now, you can write down a very analogous Hamiltonian where you replace the IR phonon just with the electric field coming from the cavity. And you can see on a kind of heuristic level that if we can make this E squared term finite and large, it should have the same sort of effect on the Raman phonon as the nonlinear or the driven nonlinear system. So this is exactly what we did. We tried to evaluate this E squared term, and the system we did it for is the surface modes of strontium titanate, which is a paraelectric material. So basically, you can write down the quantized electromagnetic modes, and you can evaluate these electric field fluctuations. And what you find is an expression of this form where you basically have the energy of the surface mode divided by the cube of the distance to the surface. This actually seems to be a rather universal form for the fluctuation. So we did it also for a Fourier-Perot cavity, which is a very different sort of cavity, but we still get the same kind of expression of some characteristic frequency divided by a characteristic volume, which in that case is the spacing between the two mirrors. But the key feature here is that if you do this for a surface mode, omega and D are decoupled parameters, so you can tune them independently, and you can actually make these fluctuations very large. So if you look at the fluctuations a distance 5-6 nanometers away from the surface, this almost approaches the typical field strengths that you get in driven terahertz experiments. And therefore, we would believe this to induce a finite effect. There are two things I would like to mention here. One is that this is a highly off-resonant effect in the sense that these local fluctuations involve all the modes of the cavity, and to get a finite effect, you need to sum over all the full mode structure of the cavity. This is necessary in order to cancel this 1/volume scaling that you trivially have in the mode functions and in the light matter coupling. So this is also a highly collective effect, which gives rise to this finite term.
But why is surface important? And why wouldn't I get the same effect if I just had something that's embedded inside bulk strontium titanate?
So these surface modes are localized at the surface, and you get a very high density of states at the given. I don't know if I have the density of states here now, but you get a very sharp peak in the density of states. So you get a lot of modes kind of acting collectively at that frequency. If you compare that with the case of the Fabry-Perot cavity, where the density of states is spread out over all frequencies, basically, you see a much smaller effect for the Fabry-Perot. So I think that's the key feature. But I'm not sure it needs to be a surface, but it needs to be some sort of sub-wavelength cavity, probably, where you really squeeze a lot of modes into finite frequency range.
Because the LO phonon in strontium titanate is basically dispersionless. So, but anyway, all right, let's discuss this later.
Yeah, that's a good point, actually. Yeah, so just to wrap this part up, what you can do then is to, we have shown previously that this material FPS is described by a Ginzburg-Landau theory of this form, where now you can also add this coupling between the electric field fluctuations and the Raman mode. And if you stretch this Raman mode, it induces or introduces a finite magnetization. So this is an antiferromagnet in its ground state. But if you have this coupling and you're close to the transition temperature, this induces also a finite ferromagnetic magnetization, which is then scales with the distance between the material and the substrate. Yeah.
Basic question: how is you know how the distance iron, phosphorus sulfide, and
that you would have to do with some sort of spacer, I guess. So I'm not sure how it would be done in practice. I mean, HBN maybe, or something else, which is, it should be something which is transparent at these wavelengths. Yeah.
Well, symmetry, because magnetization rate is more than the time inversion, and your phonon Q should be even. Are we allowed to have M.Q coupling?
Yeah, so actually, yes. I mean, this you have to consider the full point group symmetry, but as far as
Break time reversal?
Yeah, I mean, it doesn't break time reversal symmetry in the antiferromagnetic state. Well,
Wait, I'm sorry, what's L in this?
This is the antiferromagnetic order.
All right, so both L and M are time reversible.
L,
I think it's the same.
L is antiferromagnetic.
Yeah, no, that's true. Yeah, we checked this also together with Marius, and we came to the conclusion it should be fine. I don't remember the precise transformations now.
L is antiferromagnetic.
Yeah. Okay, so what we would like to do now is to consider an open cavity system, such that we can probe these sort of cavity-induced effects. Yeah.
Sorry, I just had a quick question. So this kind of E-squared expectation value that you're using to tune the phase, I mean, even without the presence of a phonon, if I just put the material over, some distance from a dielectric, there's also a pretty strong contribution there because of image charges. Have you looked at kind of non-resonant materials, so like non-phononic surfaces and stuff like that?
We haven't looked at that,
okay.
but it will be interesting to do. Yeah. I mean, one interesting thought example is like it's known that if you, or at least proposed that if you put strontium titanate itself inside a cavity, you can drive it from the paraelectric to the ferroelectric phase. So if you would use now strontium titanate as a substrate and put strontium titanate on top,
Yeah.
what should happen.
Or any dielectric. You can even pattern the dielectric in order to tune the distance between different parts of the material and the surface and change the local kind of Casimir forces on this surface.
Yeah. Now, so this is just one example. But I would like to stress, the generality of this is basically that if you have any type of nonlinear photonics effect, you should be able to realize the same effect in equilibrium by coupling to electric field fluctuations that you can do by driving an IR mode out of equilibrium.
Is there also an effect if you just have a Q dot E coupling, say at higher order in lambda or something like
It should be then a second order effect, I guess, because to linear order, E is just 0 in the vacuum. So it needs to be at least quadratic in the E field. No. Okay. Yeah, so what we want to do now is to see if we can use this kind of cavity theory to also look at open cavity systems where we can introduce and remove photons. I mean, both to pump the cavity and to learn something about what is going on inside the cavity. So the framework that we have tried to develop is basically based on the same sort of theory on the matter, or I mean, on the cavity side. So we want to include strong matter correlations and strong light matter couplings, and therefore we want to be non-perturbative in the light matter coupling, which you can do by using these cavity Schrieffer-Wolff transformations. But we also want to be in a limit of kind of high quality cavities, such that if you introduce a photon into the cavity, it bounces around many times before it leaves. So that means we're in a regime where this coupling between the outside and the inside is very small, and we can try to think of developing a perturbative treatment in gamma, which is the coupling. And this can be done with an input-output theory. Did we miss? Okay, yeah. So basically, what the system we're trying to consider now is a general system where we have some matter Hamiltonian with the light matter coupling and some cavity field. So this will be, the inside system or the cavity. And then we're coupling this to a photonic bath outside via some factors gamma. And just following standard input-output theory, you can define an input field and an output field that lives in the distant past and in the distant future, and derive a relationship between the output field, the input field, and the fields inside the cavity. So formally then, if you know what is the input field and you can calculate what is the response of the cavity field, you get your output field and you can probe the cavity with such a setup. So specifically, we're gonna start looking at coherent input states. And when you have a coherent input, you get this very simple relation between the output fields and the cavity fields, where these are so-called fluctuation expectation values. So if you can calculate the correlation functions of your cavity system, you directly get your correlation functions of your output system. However, this cavity field implicitly depends on the input field, and we somehow need to decouple these. So what we do is, again, to use a kind of Schrieffer-Wolff transformation. So we do a transformation on the Hamiltonian to decouple the charge and spin sector. But this also introduces a shift of the cavity operators and gives you these terms which couple light and matter, such that if you probe correlation functions of this A, you implicitly also probe correlation functions of this matter operator S. Now, formally, this cavity field is coupled to the input field via the equations of motion. But here we're to lowest order neglecting this input field term and looking at the vacuum contributions. And the systems that we have been looking at so far are these simple Hubbard-like systems where you have some kinetic terms, some external magnetic field, and some Hubbard on-site coupling. So to start with, we look at the simple Hubbard dimer. Yeah.
On the equation of motion you have for the cavity,
Yes.
should there be a damping term for the cavity also corresponding to the leakage from the cavity?
Yeah, that should enter via the commutator.
Okay, that's it. That's
Yes.
I see. Okay.
But that's true. Yes.
Okay.
But shouldn't the damping term be dissipated, so it shouldn't enter?
Sorry.
Damping term be dissipated, so it should not enter in a Hamiltonian for the cavity, but there's some.
Yeah. So maybe that is missing then here. But yeah, there should be a damping term also coming from the coupling to the bath.
Well, it just comes from, I mean, if you keep the cavity and the output fields, and then you eliminate the output fields, you get the damping and the Langevin term that you wrote down.
Precisely, yeah, but the damping would be part of only in each cavity, right? But
Oh,
it's
yeah.
separate.
Right, there needs
Right,
to
it's
be
part
a
of the
lead out
coupling.
in those equations.
Yes.
If you're gonna go that route. Anyway.
But yeah, you're right. It should be there. Yes. So what we've been looking at now is just a simple Hubbard dimer, which would act as a very simple model for a hydrogen molecule. So we have basically two spins, which then where an electron can hop back and forth between these two sites and give rise to an exchange interaction. And then we're looking at what happens with the cavity state as we tune this magnetic field B. And what we see is that for small magnetic fields and for not too large interactions, the ground state of this hydrogen dimer is an entangled state, while if you crank up the magnetic field sufficiently, you go into a polarized product state and you lose the entanglement. And this is actually reflected in the cavity occupation, as you can see in this figure down here. So S is the entanglement between the two sides of the dimer. Okay. There should also be a density here, but yeah, so the density also, you can see it up here. And then the density drops down from being finite to being exactly zero as you go across this transition. So the cavity photon number in this sense probes this entanglement transition. Yes.
Length of the drive.
Here, there's no drive. This is just a vacuum.
Then Hilbert space is basically two states.
Plus the photons. So we have a photon inside or we have a cavity field.
No, but the matter is two states, right?
Four. So it's two electrons on two sides.
But not all of them coupled to light, right?
Yes.
But so just S that S.
Yes.
Then I would expect just a Jaynes-Cummings ladder.
For the density or for the energies.
Four electronic states,
Yes.
two only coupled to light,
Yes.
like a dipole.
Yeah. Yes.
Then I should have the same.
But we have a highly nonlinear light matter coupling, so it's not this linear.
The Jaynes-Cummings Hamiltonian. Jaynes-Cummings one.
In the Coulomb gauge, you mean? I mean, it's not a linear light matter coupling. It's all the non-rotating wave effects, and it's if you write down this Peierls coupling, it basically includes photon effects to all. We don't expand the Peierls, no.
But if I had done PCW, then it would be.
Yeah. There's actually a lot of subtleties with doing that, which would be nice to discuss later. But this is something that Lucas is working on at the moment. But yeah, in principle, you could do that transformation. But then you also need to be very careful with other things. But yeah. No, so this is just a vacuum effect. What we're doing here is just to look, at how certain cavity properties change as you go, as you tune the parameters of the Hamiltonian.
But wait, is
But then here you can also compare. Sorry.
I just want to be sure I understand what you mean by entanglement phase transition. As I increase B, at B equals 0, the ground state is just a singlet.
Yeah.
As I increase B above some value, the ground state becomes a triplet.
Yeah.
And because the ground state is a triplet, then it becomes completely inert up to the scale of U for any charge fluctuations. So that's the mechanism for what you mean. Okay.
So it's trivial in the sense, yeah.
I don't know what's going on.
No.
Let's not put adjectives. I just want to be sure I know.
Yeah. But yeah, you're right. Yeah. And then we've also checked that, okay, these calculations are done, as I said, just in the cavity vacuum. But if you do this in a driven system as well, you see exactly the same effect. So here we show the cavity photon number as a function of time and as a function of magnetic field when you drive the system. And you see exactly the same sort of transition going across this critical magnetic field. So it seems like if you don't drive the system too hard, looking at the vacuum expectation values and looking at the driven expectation values basically gives you the same for this system. All right. Then we've also tried to look at correlation functions. So, I mean, we just define any correlation function, a 2-point correlator like this. And then via these Schrieffer-Wolff transforms that I showed you up here, you can kind of connect correlation functions of the photon field to correlation functions of the matter field. So if we do this, we find, for example, that the photon number autocorrelation function is proportional to the dimer-dimer correlation function. For these G1 and G2 functions, there's not such a simple analytical relation, but we can still compute them numerically. And what we find very generally is just that these cavity correlation functions, they probe the hybrid excitation spectrum of the system, which is kind of what you would expect. So, I mean, you have these energy denominators, which give you the energies of the hybrid system. And then, of course, you will modulate the matrix elements on top, corresponding to each excitation, depending on which operator that you couple to. And these vacuum correlations, at least the G1 and the G2, could in principle be sampled via electro-optical sampling. But one can also get the real or the same correlation functions in a really driven system, which is discussed, for example, in the work of Martin and Spencer, that I guess we will hear more about later today. And it's also possible to formulate this input-output theory as an S-matrix theory, which Mohammed has been working on.
Mentioned you can measure the vacuum correlations using electro-optical sampling. So
yes.
Suppose I was an experimentalist.
Yes.
In the other cavity material. So what would I actually do? So what's the
For electro-optical sampling?
Measuring the vacuum fluctuations using your.
So you can measure the fluctuations of the electric field, as far as I understand, with electro-optical sampling.
There. So how would that look like in practice?
So basically, you have your cavity field, and then you send a weak probe pulse at some other frequency through the cavity, and then you look at how the polarization changes of that probing field.
But in your theory, there is no probe pulse, right? Because you explicitly assume that the input field vanishes. So you're
sure, but you can show that this theory exactly gives you the electric field fluctuations of the vacuum if the probe is weak enough. So this electro-optical sampling can sample properties of the vacuum fluctuation.
I'm not sure this is right. So if you have a strongly coupled cavity matter system,
yeah.
you start putting photons into the system, right? Yeah. That state will generally change.
Yeah, it depends on how many photons you put in there, I would say.
Even if you dump in few photons,
yeah,
appreciable should happen to the matter field from vacuum fluctuations. Yeah. Certainly adding photons into the system.
Maybe we can discuss this later, because I think, that will not be the case in any realistic scenario, that if you just add 1 or 2 photons, something will dramatically change.
Agreed, yeah, but then wouldn't the vacuum fluctuations also not do anything?
But in the strong coupling, large, your camera is small.
Sure. Okay, so there are subtleties with this that I would love to discuss, because I think this is an effect of this. Yeah. I think this is an effect of this so-called, single effective mode approximation, where you basically sum up a macroscopic number of modes and you put them into one frequency with one light matter coupling constant. But that also means that if you start populating that mode with, let's say, 1 or 2 photons, that's not like putting one single photon into your cavity, because it's spread out over a macroscopic number of modes.
But then the model is not accurate because timer. Timer, then it's like a little atom coupled to a cavity, and then Van Leeuwen can tell us, for days what happens over there.
Yeah.
You still see like effects to the dipole coupling to the vacuum, but like it's a linguistic problem that people call this the vacuum Rabi splitting. It's really like the single photon Rabi splitting. That you can't know anything about what the vacuum is doing without putting like a finite field in there that has like a.
Sure. No, I mean, I agree with that. You need to put a finite field through. I guess the question is, how much are you perturbing the ground state then?
It's just separating those two things is, I think, the mental problem that.
Yeah. Okay, but yeah, as I said, I'm happy to discuss this further. I just want to mention now we're also doing this. I guess I'm running out of time, so you can also do this properly just with driving the system externally, like you would do with a laser field, and formulate this as a kind of master equation with a Lindblad operator. What happens on a classical level is then that when you pump the cavity, you enhance the internal intensity by a factor which is proportional to the finesse of the cavity, such that you can generate larger effects inside a cavity than you could otherwise. So, for example, if you look at the Rabi splitting of a two-level system as a function of cavity outside coupling, this is an increasing function as you crank up. Well, it's 1 over gamma, but yeah, no, it's gamma. Yeah. So as gamma becomes smaller, this F becomes larger, and you get a larger splitting with the same driving fluence. And similarly, if you drive phonons inside a cavity or in free space, you can generate a much larger phonon displacement by this intensity amplification effect. So I would just, I mean, I don't know how much time I have, like maybe 5 minutes. I will just mention some ideas we have trying to go forward, which goes more in the direction of the topics of this workshop. So this is kind of how we can probe and tune properties of cavity matter hybrids, and how we can use these cavity matter hybrids to generate non-classical light. So I will just run through these very quickly then, but one thing that comes out of this input-output theory is that basically when you're probing photon correlations of the cavity, you're probing dynamical susceptibilities of your matter system. And there's this paper from the group of Peter Zoller from 2016, where they show that if you probe dynamical susceptibilities of an observable which is relevant at the phase transition, or rather a quantum phase transition, that's actually like probing the quantum Fisher information of that observable. So this is something one could think about also in the cavity context, how this would generalize. If you can drive a quantum phase transition via the cavity matter coupling in this sense, how would that be reflected in the quantum Fisher information for your cavity observables? And in extension, would that also be somehow reflected in the emission properties, or the photons being emitted from the cavity? Another point I would like to mention is that these effective theories for spin photon systems, for example, they become highly non-local when you do the perturbation theory to higher orders. So if you do the second order Schrieffer-Wolff transformation, you just couple spin flips locally. While if you extend this to third or fourth order, you start to couple spin flips in vastly different places of the sample. And this is because the cavity field lives everywhere. So if you do a spin flip here, that can be coupled to a spin flip in a different part of the sample via the cavity field. So by extension of effects like this, it would be interesting to think about, first of all, can you engineer long range and non-local interactions inside the cavity to enhance frustration of the system? This was discussed in this paper here as a possible route to realizing quantum spin liquid ground states or steady states. But also if you have a coupling between the cavity field and some very non-local matter operator, can you somehow use that to read out topology of systems where you don't really have a local order parameter, such as these Kitaev systems?
Wait, I'm sorry.
Yeah.
What's the idea for reading out topology?
Well, what you would need to do if you want to probe something like this Wilson loop operator or...
Yeah, but I'm just wondering if you...
I don't have a concrete idea.
Which is an all-to-all coupling.
Yeah.
Okay, all right.
So my idea, if I'm expanding a little bit on it, so what we find is typically that one photon operator couples to two spin operators. So if you would look at the 6-point correlation function of a Kitaev system, you would have these 6 spin correlation functions. And then in the Kitaev system, it's known that these are extremely short range, so you can only couple in a certain way. So what would be interesting, for example, to do is to try and work out these 6-point correlators and see if you can match that to a photon operator. That would be one idea. Yeah. Yeah.
For this, you don't need to be in the strong coupling regime, right? You want to be in the weak coupling regime. You don't need to be in the strong coupling.
Yes, yes.
With the strong coupling, then you may actually change the underlying state.
Yes, yes. It depends on what you want to do. I agree. Yeah. This, I think I'm skipping over. Yeah, okay. And then you can also think of kind of inverting the scenario and see, can you use the cavity system somehow to generate non-classical states? So it was discussed in this paper by Levenstein from a couple of years back that if you do high harmonic generation of a coherent state, you generate a new coherent state with a slightly reduced amplitude. And then if you do a post-selection measurement, which acts like a projection, you can generate cat-like states, which are basically then a linear combination of these two coherent states. And the Wigner function of this cat-like state is shown here. So one thing one could also imagine thinking about is if we can somehow increase these nonlinear light matter coupling processes inside a cavity. And basically increase the efficiency of processes like this. And then the final thing I would like to mention, is again about trying to generate entangled photon states. So coming back to this connection between the quantum Fisher information and the dynamical susceptibilities, if you would take a system and tune it close to a phase transition, where the quantum information becomes large, meaning that you have large entanglement in the system, how would the entanglement structure of this emitted field look like if you're sending photons through that system? This is, I think, something that also Martin will discuss later today. And also, can you use cavities somehow to increase optical nonlinearities in such a way that you can amplify spontaneous parametric down conversion processes? This is something we've been discussing a little bit with Nick. For example, if you can do this by using strong phonon nonlinearities inside the system and then driving it. Yeah. So that's the talk. Thank you.
A couple of minutes for questions or comments.
You had a slide where you were showing how various intensity correlation functions map to spin correlation functions. Did you look at quadrature correlations also and what you could get from homodyne type measurements?
Well, but we should.
I was just gonna follow up on that. Like, so if you take like a boring laser, maybe you do single atom strong coupling, you drive it at the point where classically you would have bistability, but now you get like a change in the transmission because you saturate. And if you look at the P function or the Wigner function, positive probability distributions, which are just given by homodyne or heterodyne detection.
Mm.
You do see signatures of like transient or intermittent entanglement at that region. Can we just adopt those kinds of techniques to here? Just
yeah, I think that should be.
simple as that, or like?
I mean, I don't know the details of these setups, but in principle, yeah, I think it should be possible to adapt this.
Talk a little bit about that.
You will talk about it. That's the idea. Yeah, make you realize that. Okay.
Flux operators in G-type systems, the 6-spin operators would be exceedingly interesting to do for systems like ruthenium tactoride.
Yeah.
Show this physics of the magnetic H structure directly.
Yeah, this is something we really want to do. So it would be great to discuss, if this is possible.
How does one measure them?
Those flux operators. I mean, the proposal I had here was basically to try and see if you can find certain photonic observables then that would be sensitive to this flux structure.
What are these observables?
We don't know yet. I mean, I think it should be some sort of 6-point correlator.
So as a teaser again, I'll show the 3-spin operator.
Yeah.
How that can.
Yeah.
So
we just have to add 3 more. Yeah.
You need to multiply by 2.
Yeah. Yeah.
That's already painful.
Yeah. Yes.
Spin correlated.
Okay. Thank you.
I think this is a good point to move, and then thank Emil.